Good day, everyone. We are the Group 1. I am Angel Grace Balaes, together with my group mates, Jera Monsanto, Hervey Jimenez, Stephanie Sarkis, Christine Paigalan, John Macale, and George Labis. And we will be discussing to you about 3D Geodetic Network Adjustments. Next slide. A 3D geodetic network uses observations such as distances, angles, and satellite measurements, like GPS or GNSS, to determine the coordinates of points in three dimensions, the X, Y, and Z, or the northing, easting, and elevation. Since field observation contains errors caused by instruments, atmosphere, or human mistakes, adjustment is needed to improve accuracy and consistency. This will be the outline for our discussion. Main purpose of 3D geodetic network adjustment is to improve the accuracy and reliability of survey measurements. The process uses least square method to properly distribute errors and determine the most probable coordinates of all points in the network. These are the objectives of the adjustment process. 3D geodetic network adjustment has many real-life applications. These include GPS control surveys, engineering projects, construction monitoring, land surveying, and deformation monitoring of bridges and dams. In 3D network, different coordinate systems are used such as geographic coordinates, geocentric coordinates, and local coordinates. These systems are related through transformation matrices, allowing surveyors to convert observations from one coordinate system to another. This slide explains reduction of observations. The local geodetic coordinate system converts observations into usable forms. Observations include slope distance, azimuth, and vertical angle. Equations are then used to relate these measurements to northing, easting, and elevation values. And this process prepares the equations needed for the least squares adjustment. Now, let's discuss the inputs required in the adjustment process. The first input is the observation themselves. These include horizontal angles, vertical angles, slope distances, and GNSS baselines and height differences.
For the continuation, the control points coordinate. These are known reference stations with fixed coordinates that establish the datum or reference. These are initial estimated coordinates assigned before adjustment begins. So the process also requires weight matrices, stochastic models, and datum information. So for the weight matrix and stochastic model, it describes the reliability of observations. More accurate measurements are given higher weights, while less accurate observations receive lower weights. The stochastic model defines the statistical behavior of observations, including variance, covariance, and standard deviation. Datum information is necessary because the network must have a fixed orientation and scale. The datum is used to fix control points, define the coordinate reference system, constrains the network, and maintain consistency of coordinates. So without the datum, the network would float, meaning the coordinates would not have a unique reference system. And for the outputs, we have five outputs. First is the adjusted coordinates, adjusted observations, residuals, precision measures, and error detection result. The type of least squares equation is used the linearized least squares observation equation. So, as we all know, this is the general equation where V represent the residual vector, A is the design matrix, and X represent the unknown coordinates. So, kining equation nagrelate sa observation errors to the correction needed for the coordinates. So, the least square method minimizes the M inverse V transpose, where P is the weight matrix. This means that the adjustment minimizes the weight sum of squared residuals. The method ensures that the final coordinates become the best possible estimate based on all available observations. So, mo ni ang normal niya nga equations.
So let's talk about general workflow for adjustment of 3D geodetic networks. So there are three steps for field observation, and first is to surveys collect measurements using total stations, GNSS, receivers, and levels. And step two is preparation of data, which is the observations are checked for completeness and consistency. And step three is formulation of observation equations, and is formulation observations. It is a mathematical model relating observations to unknown coordinates are formed. Example is include distance equations, angle equations, and GNSS baseline equations. Step 4, since many observation equations are nonlinear, they are linearized using partial derivatives. The design matrix A is then formed. And step 5 is least squares adjustment. The normal equations are solved to compute coordinates corrections. And step 6, it is accuracy assessment. Residuals and covariance matrices are analyzed to evaluate precisions and detect possible errors. And finally, step 7 is presentations of final results. The adjustment coordinates are statistical reports are then presented and evaluated. And to conclude, 3D geodetic networks adjustment is an essential process in modern surveying and geomatics. It ensures that survey measurements become accurate, reliable, and consistent By applying the least squares method, errors are minimized and distributed systematically throughout the network. The process plays a very important role in engineering, mapping, GNSS positioning, construction monitoring, and geodetic control surveys. Without network adjustment, survey measurements may contain inconsistencies that could affect the reliability of maps, structures, and position system. Thank you for listening.